Okay, let's start the second Hermann lecture by Hiroshi Oguri. And she gave a really beautiful, nice talk. And we would like to listen to the second one for two exact results on 2D CFT. So,
thank you very much. So, thank you for the introduction. So the title of my talk is Two Exact Results in 2D CFT. Since there are some mathematicians, so I need to clarify the title. So the BCOB paper that Professor Yao generously introduced yesterday, the title of that paper was Exact Result in Quantum String Theory. So I use the word exact in the same sense that I used in the BCOB paper, which is that in that paper, we made lots of conjecture, which from the point of view of mathematicians have not been proven. But we actually at least made precise statement which can be checked mathematically. So it is in the same sense that I propose exact result into the CFT, that these are exact statements, and I give you physics reasoning for these statements. Whether these are true mathematical statements or not is something that can be checked more rigorously, but at least I can make precise mathematical conjecture. Okay, so I'd like to present two inequalities, and these are the inequalities that I would like to explain in this second lecture. Oh, by the way, I forgot to say that the first lecture, I was told the first lecture is for general undergraduate mathematical audience, and this can be more technical. So in the first lecture, I gave talk about my work that ranges a long time, starting from my PhD thesis 35 years ago. But today I only talk about work I did within the last year. And in fact, both are published this year. So this is quite recent. And the first, I would like to talk about this inequality. And the second, I would like to talk about this inequality. Okay, so delta, so these are both about two-dimensional conformal field theory. Delta is a conformal dimension of some scalar field. T, and I assume that there is going to be a modularized space of conformal field theory. So I'm assuming that there is a continuous family of conformal field theory. And T is a parameter. And in fact, it's a geodesic distance on the conformal manifold, the modularized space of conformal field theory. And there is this equality like that. There is a case when conformal dimension behaves like exponentially in the distance, and we can bound this coefficient in this way. So I'll explain what this is. And in the second part of my talk, I will give you inequality, which has to do with the interface between two conformal field theory. When you have two conformal field theory, you can sometimes consider interface between them, which preserve one half of conformal symmetry. And there are various quantities that characterizes in interface. And in particular, this quantity C left, right, and C effective are two important quantities that characterize the interface. And I'm going to present inequality between them, okay? So that's sort of content of my talk, okay? Is there any questions so far? I haven't explained these quantities, but at least I hope it's clear what I'm going to aim at, okay? So let me first talk about this inequality. So here is actually the statement I would like to make about this inequality. So this is my work with Yifan Wang, who is at NYU, posted in May this year. So let's consider any unitary two-dimensional conformal field theory. I assume there is a vacuum state in the conformal field theory. Energy is bounded from below. And I assume the spectrum is discrete. Okay, and then supposing there is a modularized space of this conformal field theory. Suppose there is a continuous family of conformal field theory. These days, this modularized space is called conformal manifold. So conformal manifold is a technical term which basically means modularized space of conformal fields. Okay, so suppose there is a scalar primary field whose conformal dimension, scaling dimension delta, vanishes at some point on this conformal manifold. Then Yifan and I prove the following three statements. One is that the distance to that point where conformal dimension vanishes is infinite when you measure it in terms of Zamolodchikov metric. Zamolodchikov metric is a very natural metric you can define on the modularized space of conformal field theory, determined by two-point function of exactly marginal operators that generate the deformation. We also proved that the approach to this limit is exponential, with t being the Zamorodnikov distance, and alpha is some positive constant. And moreover, we showed that this alpha satisfies this inequality. We have also clarified exactly what happens if you go to this limit, and I will tell you more about it later. So I have some sentences here, but I will explain what this is later in this talk. Okay, so this is what I would like to present in the first part of this talk. Okay, I hope this is clear. So this is supposed to be mix of physics and mathematics audience. And so I would like to give you physics motivation of why we thought this question is interesting. Okay, so in physics, we think that the physical world has hierarchical structure, that in each scale, there is particular laws of nature. And if you go to more and more microscopic world, you get more and more fundamental laws of nature. So that's sort of our expectation. So we have this notion of low energy effective theory. And low energy effective theory is very useful. When you don't know about more fundamental theory in ultraviolet, you can parameterize your ignorance using low energy effective theory. But sometimes we have to be careful. We need to make sure that you are not parameterizing an empty set. You need, sorry? So non-gravitational system, actually, we don't have to worry about this kind of a situation, because there is actually a standard understanding that you can essentially write down any low energy effective theory that's consistent with symmetry, and you can expect it to have a consistent ultraviolet completion. In the last few years, it has become increasingly clear that this is not the case with gravity. That if you include gravitational degrees of freedom, the separation of ultraviolet and infrared degrees of freedom fails with gravity. I mentioned some of this feature yesterday in my talk because of the black hole. And so, for example, the radius of the black hole horizon grows with energy, which is opposite of UV-IR separation. So for gravitational system, it has become clear that there are constraints on their low energy effective theory that cannot be captured by the standard Wilsonian paradigm that you can write down any effective theory. And so this leads to the idea of swampland as opposed to landscape. And so this was advocated by Cameron Buffer. And there are actually two main lines of this swampland idea. One is the absence of arbitrary parameter in quantum theory of gravity. And this can be actually quantified and made more precise in the form of distance conjecture. There is also this idea that quantum theory of gravity has no global symmetry, which can be made precise in the form of weak gravity conjecture. Okay, so these are actually the date where, as far as I can tell, those statements was first made. Okay, so can you guess what this date is? And so let's first start with absence of arbitrary parameter. So to my knowledge, the claim that the quantum theory of gravity or the ultimate unified theory has no parameter was first made in the autobiographical note of Albert Einstein in 1949. So this is actually very interesting reading. And in one of the chapter, he introduced a notion of natural unit. So if you're a physicist, you know what natural unit is. If you're a mathematician, you may not know. But there are three important fundamental constants in nature: the Newton's constant for gravitation, speed of light, and Planck constant, which characterize the size of quantum effect. And if you use these three quantities, you can actually measure any physical observable in terms of this combination of these numbers times some dimensionless constant. So this is called, so that's a unit in which all these constants are set, fundamental constants are set equal to 1, called natural unit. So he introduced this notion of natural unit, and then he says that if you write down basic equations of nature or physics in terms of natural unit, then any parameter in the theories are dimensionless. So he says that only dimensionless constant means parameter in this case, can occur in basic equation of physics. But then he went on to say, concerning such, I'd like to make a theorem, state a theorem, which at present cannot be based upon anything more than upon a faith in the simplicity, namely intelligibility of nature, that there are no arbitrary constants of this kind. So he claims that if you consider fundamental laws of nature, then there should be any constant. Okay, so now Qumran and I actually made a little bit more sort of modern fashion. So we reformulated his claim in the form of conjecture 0 in the distance conjecture. And we claim that every parameter in quantum gravity is an expectation value over some dynamical field. And in particular, this means that you can vary that by changing the expectation value. So any constant, what seems like what constant of nature can actually be varied in some particular configuration. Okay, actually, I can prove this in ADS-CFT correspondence. So if you assume that ADS-CFT correspondence as a fundamental principle of quantum gravity, then we can actually prove this at least for quantum gravity in anti-eta space. Okay, so let me give you the proof of this statement. Okay, proof in the sense of physics, not mathematical proof, but physical proof. Okay, so here is an idea. Suppose somebody give you a gravitational theory in anti-eta space, and suppose this theory has a parameter called that lambda. I'm assuming here only continuous parameters. There can be discrete parameters that should be discussed separately, but let me first only consider here, for the purpose of my lecture, that there is a continuous parameter in quantum gravity. So you have some kind of Lagrangian density in anti-eta space with parameter lambda. So that means that according to ADS-CFT correspondence, there is also conformal field theory on the boundary of anti-eta space, parameterized by the same parameter lambda. So you might consider changing this parameter because you have continuous parameters, so you can vary that. But then we know in conformal field theory, if you vary the continuous parameter, the Lagrangian density is modified by some small number multiplied by exactly marginal operator, which is a scalar field of dimension 1, 1. But then, according to the ADS-CFT dictionary, if there is exactly marginal operator of dimension 1, 1, there is actually a scalar, massless scalar field in anti-eta space, so that this parameter is evaluated by the expectation value of the field. So this is actually what Einstein conjecture, that any parameter in the theory is the expectation value of some field. Okay, so this is a proof of this conjecture. Okay, well, to be precise, this is not a complete proof because the claim that the deformation, continuous deformation of CFT is caused by exactly marginal parameter is actually a conjecture about conformal field theory if you are more rigorous algebraic quantum field theorists. So in fact, Shota Komatsu, Yuya Kusuki, Marco Maineri, and I are working to actually prove this, and we have almost proven this statement. So we hope to publish this very soon. But modulo this is a proof. So so this can be, so therefore this statement that every parameter in quantum gravity is an expectation value of a dynamical field and can be varied by changing the expectation value is actually a exact statement in quantum gravity in anti-eta space, which can be proven using ADS-CFT correspondence. And this can actually be put in a more sort of broader context in the following sense. That for the last decade, we have learned that the notion of global symmetry in quantum field theory can be greatly generalized compared to what we had known before. So for example, there is a notion of p-form symmetry, which means that the net charge or topological defect associated to the symmetry has codimension p+1. So what used to be called symmetry in nature is now regarded as zero-form symmetry, because so what does Neta theorem that we learn in quantum field theory course is a charge which is given by integrating the Neta density or Neta current over the Cauchy surface. But Cauchy surface is the codimension 1 surface. And there is a generalization of that where analog of Neta charge is now integral over codimension p+1 surface. There is also a very interesting generalization called non-invertible symmetry, which is where the topological defect, the generalization of nature charge, does not form a group anymore, but makes more in general an algebra. So in this language, the absence of parameter in quantum gravity can be regarded as absence of -1 form symmetry. So in that sense, these two statements, absence of parameter and absence of global symmetry, can be unified in this generalization of symmetry. Okay, so it's natural to ask where this refined version of this conjecture can be also be unified. And I'll come to that in the next slide. So the unification means that now this parameter alpha has to be bounded by some inequality. And that's what we have achieved. That's what I have done with EFAM1, at least in the case of ADS3. So before we get there, I'd like to note that even though in ADS we were able to prove this statement, but this is actually not a useful statement if we want to understand quantum gravity, because it does not provide useful constraint, since what appears to be parameter in low energy theory may actually be fixed by some unknown dynamical effect in high energy, such as some potential in the high energy theory. So for example, we know that the standard model of particle physics has 19 parameters, such as the mass of quarks or mass of electrons or Higgs coupling or gauge coupling. So there are 19 parameters in standard model. And in fact, we also know that the neutrino has masses. So that adds 7 more parameters in standard model. There is a standard model of cosmology. It's called lambda CDM model. The CDM means cold dark matter plus cosmological constant. Lambda CDM model has 6 parameters. But we don't say that these are in swampland, of course. These are actually model of nature. And we expect that these 19 parameters or these 6 parameters are actually expectation value of some dynamical field in the sense of distance conjecture, but they are probably determined by some unknown dynamical effect in high energy. Okay, so therefore appears to be a parameter. So this conjecture by itself is not useful. So Hermann and I wanted to make more useful conjecture. So what we did was to study known construction of string compactification on Calabi-Yau manifold in various setup, and then deduced properties that we can sort of generally state. And one statement is that if there is actually a continuous parameter, then there is always a direction which goes to infinite distance. So for example, if you have a Calabi-Yau compactification, there is always one direction where that is infinite, which is the volume of Calabi-Yau becomes infinite. And if whichever direction you go in infinite distance, we also observe that low energy effective theory is always broken if you go in some distance. And the way it is broken is that you have actually a power of light particle coming out. So these are 2 conjectures, and this can be made more precise in the following way. So the zeros conjecture I already mentioned. The first conjecture is that if you choose any point in the moduli space of string compactification or quantum gravity, then if you choose any positive number phi, there is always another point such that distance from this point to this point is greater than phi. So this is the first statement. The second statement is that compared to the point you started out, the theory at this distance point has an infinite tower of light particle with mass starting with order of exponential of e to the minus alpha phi, or some alpha. So therefore, if phi becomes large, you get this tower of light particle emerging, and therefore low energy effective theory is broken. So this is what we conjectured in 2006. Okay, so this can be more useful because this can be used to exclude some of quantum gravity theory. But so far, there has been no counterexample. In fact, after we made this conjecture, there have been lots of study of Calabi-Yau compactifications and other examples, and no counterexample have been found. And moreover, I think we can make this conjecture even more useful if we can bound this parameter alpha. And that's what Yifan and I did in the case of ADS3. Okay, so I just wanted to make some anecdote, tell you some interesting anecdote. So when so I wrote this paper called the Geometry of String Landscape and the Swampland. This is a paper about distance conjecture with Cameron in 2006, which was published in 2006. And this is actually a tweet, or what used to be called a tweet. Now it's called the X post by Inspire, the high energy database in Stanford. So Stanford University, Stanford Linear Accelerator SLAC has this high energy database called Inspire. And sometimes it makes some ex post about interesting phenomena about citation number. So this is actually the citation number of my paper with Cameron. It's very sad. It looks very sad. Every year we only got about 10 citations. In some year we almost got no citation. It's very sad. So this was a very sad paper. But suddenly, around 2015 or 16, it shot up. And in fact, this Inspire said that they did this post because when in this year this paper reached 1,000 citations, and then they said that this paper is a sleeping beauty. So the question is, who is the princess who woke up this sleeping beauty, right? So what happened was a bicep 2 experiment. So if you have assumed distance conjecture applied to asymptotically flat space or the expanding universe, then we can actually put a very interesting bound on the model of inflation. So this is actually what Cameron and I conjectured. And so this distance conjecture claims that the range of inflaton, so if you have inflation, you need a scalar field called the inflaton, which has to change its value by the amount of delta phi. And this is the amount of delta phi measured in Planck scale. And also it has a prediction. Inflation has a prediction about a ratio. So you might have heard the word cosmic microwave background radiation, which is the light that emitted at the beginning of the universe. And this light has some interesting polarization. So this particular polarization actually have some kind of imprint of the inflation period of the universe. And very important quantity is called R, which is a ratio of tensor polarization and scalar polarization of cosmic microwave background radiation. Okay, so in this diagram, the horizontal axis is a tensor scalar ratio, and the vertical axis is the inflaton range. So if you look at this diagram, so there are two curves. One is a distance conjecture curve, which is by me and Cameron. And according to this conjecture, allowed region, the theory that is consistent with quantum gravity, has to be below this blue curve. But there's another bound called Life bound. Life is a cosmologist. And he analyzed the inflation model and said that in this diagram of phi and r, the model that is consistent with the inflation has to be above this orange line. So that means that anything that is allowed has to be between this blue and orange. Okay, so that was known. Now, around 2014, I think it was February, that I was actually a deputy dean of physical science at Caltech, my university in Pasadena. And so I was doing some work in the dean's office, and the dean of physical science came, and he said that, you know, bicep 2 has a new result that we're going to announce in one month. But Caltech is one of the players in bicep experiment. So the dean got to know the result 1 month ahead of time so that he can prepare the public announcement. And so I asked, well, what is the value of this tensor scalar ratio R? And he said 0.2. So I immediately said, and he remembers this, that, well, great, it's going to kill string theory. And you can see why I said that, because if R were 0.2, then it's right here. It's actually over here. So it's actually not compatible with distance conjecture. And so actually, the dean actually still, so Tom Sofer was a dean, but he still teases me about this. But they went ahead and announced it, well, R is 0.2. And it turns out that that was wrong, that it would have contradicted. If this was true, then it would have contradicted the distance conjecture. But what happened was that the bicep result was wrong. And it was actually, the bicep was dissected by people like David Sparger. And if you know David Sparger, that's him. And what happened was that there was a dust in the universe, like within our galaxy, there are dust. And if light travels through the dust, then polarization changes. So there was actually a confusion between the primordial polarization that was caused by the inflation and more recent polarization caused by dust in the galaxy. And that enhanced the tensor scalar ratio and made it to the 0.2. Now, actually, there are more precise state measurement. For example, this is a Planck measurement in the European satellite. And right now, the upper bound of R is here. And in the next generation of CMB experiment, like the one that is going to be launched by Cabri IPMU and JAXA in the next decade, it's going to measure, going to put up a bound over here. So it's been interesting to actually make this distance conjecture prediction more precise so that we can actually confront the experiment. But anyway, so string theory survived at this time. And that immediately sort of attracted interest in the community about our distance conjecture, thanks to this bicep experiment. And so that was what happened to this paper. Okay, so you can see that distance conjecture can be potentially interesting in applying string theory to nature. So we want to understand distance conjecture more precisely. So there is actually a very nice paper by Eric Perlmutter, Leonardo Rastelli, and collaborators, where they formulated this distance conjecture in the context of gravity ADS. And this was partially proven, but in this context, there was no bound for the alpha. So Qumran, not Qumran, the Yifan 1 and I was very interested in it, and they thought that maybe in the case of ADS3, we can make more precise bound, because in that case, the dual theory is two-dimensional conformal theory, and we know a lot about 2D CFT. So we can actually prove this statement. So that we ended up showing many things about this. As I said, we can show that if there is a point where the conformal dimension vanishes, the distance to that point is infinite, and the approach to that point is exponential, and alpha is bounded both above and below. And we can also show that this inequality is a sharp inequality, because we can construct an example where these inequalities are saturated. Okay, so this is what we have shown. And so I would like to outline the derivation of this statement. Okay. Oh, by the way, so in a gravitational dual, we can also say that this means that if a scalar field travels beyond the Planck scale, then the mass vanishes exponentially. And this is exactly what the distance conjecture claims. Okay, so in a reminder of this first part of this talk, I will first discuss the example and prove the first two statements and prove the second two statements. And so that's the first part of this. This is somebody who is measuring swampland, I think. So here is some example. The simplest example, just to get to know what I'm talking about. Here is the first simplest example. Let's consider 2D sigma model whose target is two-dimensional force. In this case, the conformal manifold, the moduli space are parameterized by two complex numbers. One is a complex structure of this two torus, and the other is a Kähler moduli. So the Morozhikov metric is given by this modular invariant metric, two copies of this. And in fact, there is a mirror symmetry connecting these two. There are lots of interesting singularity in this modular space. One is the Z3 orbifold point. These are cusp of the modular space. And these are at finite distance. So therefore, the conformal dimension cannot vanish. And in fact, you can show that there is a gap of 2/3. And it's saturated by this enhanced SU3 primary field. But you can also go to the large volume limit. And in that case, you can see that there is a Karuta-Klein mode whose conformal dimension decays exponentially and with coefficient 1, so therefore alpha is 1. So this is a very simple example. More interesting example is n equal to 2 superconformal sigma model whose target space is Calabi-Yau. So let's in particular consider quintic Calabi-Yau manifold. This is a very canonical, very nice classic example of Calabi-Yau manifold. There are lots more type of this singularity. One is a Z5 singularities, and this can be described by Gepner model. So it's you can describe in terms of this Gepner model. And this is a finite distance singularity, so there is actually a finite gap. And we can see what is saturated. More interesting is a conifold point. Conifold point is a genuine singularity. And in that case, actually, there is a continuum spectrum. But actually, continuum spectrum does not go all the way to 0. If there is a choke, I can write it, but I don't have a choke. Oh, there is a choke. So, so there is the. So if you actually write the vertical axis, the delta for the conifold, and then there is a 0. But then there is a delta equal 1/2. And then what happens is that as you approach the conifold, there is a continuum spectrum, but continuum spectrum stops at delta equal 1/2. So there is a gap. And then this is consistent with the fact that conifold is at finite distance in the moduli space. And then there is a large volume limit of Calabi-Yau manifold. And in that case, we can actually write down the Zamolodchikov metric in this way. And importantly, there is a factor 6. So alpha is not equal to 1, but is less than 1. And it's 1 over square root of 6. And I will actually explain what this 6 means later. 6 has, well, as you can guess, this 6 has to do with the dimension of Calabi-Yau manifold. We'll see that later. Okay, so let me outline the derivation of the upper bound first, and then I will discuss the derivation of lower bound later. So let me start with the simplest case when there's only one marginal operator, and that is exact, namely when the conformal manifold is one dimension. And if we understand this case, we can understand the other cases very simply. Okay? So suppose there is a scalar primary field phi whose conformal dimension vanishes at some point in conformal manifold. So now let's choose a geodesic coordinate so that this delta monotonically decreases towards that point, and it satisfies this renormalization group equation. The derivative of delta with respect to this Zamolodchikov distance is given by the 3-point function of this primary field and the marginal operator that is causing this deformation. Okay. So as you can see, by looking at this equation, so this is an ordinary differential equation, and you can see that distance to the point where delta vanishes is infinite only when this 3-point function vanishes at least linearly in delta. And in fact, I can show you more stronger statement, that is that this 3-point function decays linearly, but with coefficient 1 in this case. So therefore, if you have this, if you substitute this into that, you see that d delta dt is equal to minus of delta up to order delta. So you can integrate that to write delta is equal to exponential minus t. And so therefore, alpha equal 1. So if we want to show alpha equal 1 in this case, you just need to show that this 3-point function decays like that. And this is what Yifan and I showed. So to explain the proof, it's useful to use this global conformal symmetry. In fact, in this proof, we only use global conformal. We don't use Virasoro symmetry. So we can use just global symmetry. And by using this global symmetry, we see that if we take derivative of this operator with respect to the coordinate, then it becomes some kind of current multiplied by square root of delta. This square root of delta comes from this commutator. So therefore, if you write this 3-point function in terms of OOM, it can relate it to the 3-point function JJ bar M with extra delta. So what we need to show is that this 3-point function JJ bar M goes to 1 in the limit when conformal dimension vanishes. We can prove this using conformal bootstrap, and that's what we're gonna do. Now, in view of time, let me first give simple and less rigorous proof of this statement, and I can make this more rigorous later. But here is a proof. Here is the idea. So J become operator of dimension 1, 0 in the limit when delta goes to 0. But for finite delta, it has some other dimension. So by knowing that 2-point function of O is normalized in this way, you can show by taking derivative of O with respect to Z and Z bar. The 2-point function of J is given by this with normalization 1. 2-point function of J bar is given by this with normalization 1. And J bar is given by this with delta. This delta is related to this delta here. Okay, so this is something you can simply show by taking derivative of this 2-point function. So now let's use a conformal bootstrap. So conformal bootstrap is the following idea that if you have correlation function, you can calculate the correlation function in 2 different ways. One is the following. So suppose you have 2-point function of J bar, for example. You can calculate the 2-point function in this way, or you can calculate 2-point function in this way. Okay, and so if you sum all the states in the intermediate stage, they should be equal. Okay, so here is that equation. In the first line, I considered this channel. So you have JJ, and there is an identity exchange, and that's the first line here. So you have J, which gives you this, and J bar, which is give you this, and then there are exchange of other operators. But if you also consider first taking 2-point function of this and this with factorized with identity operator, and this gives you this one. And if there is an exchange of exactly imaginary operator, you get this one. And then there are other operators. Okay? So you compare this. This is an equation. So this should be true for any Z and Z and B and W and U. And so in particular, if you can show that all these ... terms are also linearly independent from these terms, then you can actually equate this with this one. So then we can simply get Cjj bar M to be equal to 1 because this has to be equal to this. And therefore, delta goes to this and alpha equal 1. So this is what we wanted to show. Okay. Now, this is not rigorous because we haven't shown that these terms are linearly independent of this, so we can isolate this equality. But we can actually use more rigorous proof. And in view of time, maybe I should skip this one. But what we can do is that we can construct some kind of projection operator, which project out this particular term so that this equality can be proved. Okay. Now, so I have shown that if there is only one exactly imaginary operator, then this is true. Now, what remains is the question of what happens if there are more marginal operators. Well, generalization is very easy because essentially you can do the same proof as here, except that now there are several marginal operators here. So instead of just one term here, you have this sum over all possible marginal operators here. So we have this equation. So that means, and some of them are exactly marginal, some are not exactly, some are marginal but not exact. So therefore, if you consider only exactly marginal operator, then some of this would be less than 1. So therefore, you get some kind of inequality now like that. And there is also a possibility that you don't go to the point where delta vanishes not in optimal way. So depending on which direction you go, there is an extra suppression factor. So from that, you can see that delta goes to 0 exponentially with coefficient alpha, but alpha is bounded above by 1. Okay, so this is the first statement. So now let me prove the second statement, which is that alpha is bounded by 1 over square root of C, where C is the central charge. Okay, so far I paid attention to only one scalar primary field whose conformal dimension vanishes. But in general, there can be several primary fields whose conformal dimension vanishes simultaneously. There can be 1, there can be 2, there can be finite number, there can be infinitely many of them. We don't know. I don't want to postulate in advance. We'll see after the analysis that there will actually be infinitely many operators whose conformal dimension vanishes, but that's what I'm going to show. Before that, I do not know. So let's just postulate that there are some number of them. And for each of them, define this J. Okay? Since all n's are all linearly independent for finite delta, so therefore Jn are all linearly independent before you get to that point. But when you get to that point where delta vanishes, they might be linearly dependent. There might be linear relations. So it'd be interesting to find out whether there are operator relations between them. And in fact, there are interesting ways to find them out, which is that O satisfies the operator product relations. So you can organize the operator relation between J using operator product relation between O's. So if you consider OPE of O with O, it can become also operator whose conformal dimension vanishes, but it can also go into operator whose conformal dimension does not vanish. But in the limit when delta vanishes, you can actually well separate these two contributions because they have different Z and W dependence. So you can safely restrict yourself to OPE closed among the operators whose conformal dimension vanishes. So if you write it in this way, and if you act a linear combination of del Z and del W on it, and if you take the limit where J delta vanishes, you get a linear relation like that. So therefore, for each operator product relation, you get a linear relation between J's. And moreover, if you take product of derivative operator, and then take the limit, you get this quadratic relation. If you look at this, you see that you have J times J become double pole and single pole, which is linear in J. So this has a form of Kac-Moody algebra. So you can easily see that if you take appropriate basis of J, then actually the in the limit when J, the delta vanishes, you get a Kac-Moody algebra. And by unitarity, since we are assuming that conformal cell is unitary, this F must be the structure constant of compact semi-simple Lie algebra by the consistency of the Kac-Moody algebra. But we can claim that this F coefficient has to vanish because if it doesn't vanish, you get the no-abelian Kac-Moody algebra. And for no-abelian Kac-Moody algebra, the primary field has non-zero conformal dimension. So it's contradict with the assumption that operator whose derivative goes to J has to have vanishing conformal dimension in the limit. So that means that all this structure constant has to vanish. And from that, we can deduce that this J actually makes abelian Kac-Moody algebra. But if you have abelian Kac-Moody algebra, you can bosonize. And you can write O as the exponential in this way, namely the vertex operator form. So you can see that in the limit when there is some particular conformal dimension vanishes, in fact, there are infinitely many operators whose conformal dimension vanishes because all the operator of this form has vanishing conformal dimension. And so that means that conformal field theory in the limit contains subalgebra local operator described by sigma model whose target space is flat Euclidean space. And the dimension of the Euclidean space has to be less than conformal central charge because of the unitarity. I said that the limit of the CFT is locally Rn sigma model times compact CFT because there are various interesting phenomena that I'd like to mention. One is this example of sigma model whose target space is orbifold. So let's first consider simplest case when you consider circle radius r and divide that by Z2. Okay, so in this case, what is an operator whose conformal dimension vanishes? Well, exponential of x is not good because it's not invariant under Z2 orbifold action. So we have to consider cosine of this operator. But then by following this prescription, by following the prescription I described, you take derivative of this with respect to z and define j. But then this j is actually del x times some another operator, and this another operator is sine of x over r. So if you look at this, you might think, well, this is worrisome because all these operators should vanish in the limit of r goes to infinity. This may look like that, but this is actually not precisely true, because these operators are actually at the end point of topological defect line that implement quantum Z2 symmetry. So it was actually known for more than 35 years that if you have orbifold with respect to Z2 symmetry, so in order to make orbifold, you have to first assume that conformal field theory has some global symmetry and gauge that global symmetry to make orbifold. But if you make orbifold, the resulting orbifold theory acquires new global symmetry called quantum symmetry. So here, let me explain what this is. So you have this orbifold, and in order to make orbifold, you make this Z2 action. Okay. So if you consider orbifold conformal field theory, there is a twist field. And what it does is that if you put twist field here, and if you move X field around it, then as you go over here, it becomes minus X. This is what twist field does. And what twist field has is that there is some kind of, it generates some kind of a branch cut on the worldsheet, two-dimensional surface, which creates this kind of twist over here. But you can view this in the different ways. That in the Z2 conformal field theory, there is a new quantum Z2 symmetry, for which it acts as X goes to minus, sigma goes to minus sigma. And the way it works is the following: that suppose I put new operator O tilde, which I defined over here, which is like sine of X over R. And if you move now twist operator around it, as you come over here, sigma goes to minus sigma because of this sine factor. Sine becomes minus X. So therefore, there is actually a defect line which ends on this O tilde, which flips the sign of sigma goes to minus sigma. Okay? So therefore, even in the limit of R goes to the infinite limit, this operator is not a trivial operator, but it's actually still a topological operator which is lying at the end point of this topological defect line, which implements this symmetry. Okay, so therefore, the limit is not precisely the flat sigma model, but there is some kind of topological operator remaining over here. There is another very interesting example, which was recently clarified by Shi-In at Harvard and collaborator. And it is the following things. So there is this minimal model. Whose central charge is given by 1 over 6 over k and k plus 1, where k goes to 3, 4, 5, 6, 7, 8, etc. And for many years, people are wondering what happens when k goes to infinity. So when k goes to infinity, c goes to 1. So it looks like you get the sigma model whose target space is a flat space. And in fact, it was shown by Runkel and Watts observed that if you take this limit, the resulting conformal field theory look like you have some kind of flat one-dimensional direction. But there was some funny things happening and they didn't quite understand. And this year, actually, this Shi-In and his collaborator at Harvard showed that the limit is actually this R sigma model, but with some kind of wall in the target space. And there is actually interesting Dilaton and action, there is an interesting Dilaton and tachyon profile on the wall. So away from the wall, it looks like flat sigma model, but it's not completely flat. And this is why I said that the limit is locally flat sigma model times conformal. Okay, so anyway, so away from this kind of wall or other defect, it's a flat sigma model. So you can actually estimate, using this picture, estimate how conformal dimension vanishes. And then you can actually use that to put some kind of bound on alpha. So this is how we came to this bound. Now, if you have supersymmetry, you can actually strengthen this bound by extra factor of square root of 3/2. And in fact, in the example of quintic Calabi-Yau, C is 9. So in fact, that becomes alpha equal 1/square root of 6. So the large volume limit of quintic Calabi-Yau actually saturates the lower bound of this inequality. Okay, so let me just briefly mention this the other line of conjecture. So the absence of global symmetry in conformal field theory was postulated by John Weyl. And in the modern language, we say that there is no global symmetry in quantum gravity. And Daniel Harrow and I proved this statement in ADS CFT. And we actually made a very interesting use of the relation between the holography and quantum error correcting code. But in view of the time, maybe I should skip this. Just like the absence of parameter in quantum gravity was sort of quantified and strengthened by the distance conjecture, the absence of global symmetry in quantum gravity was strengthened in the form of weak gravity conjecture. That is, that any low energy theory describing the Einstein gravity, Maxwell field, and the finite number of matter field, if it has ultraviolet completion as a consistent quantum theory, there must be a particle whose charge and mass is less than Planck scale, such that this inequality is satisfied. So this is a weak gravity conjecture. So we are trying to formulate and prove the corresponding statement in ADS CFT. And given that distance conjecture can be proven, I think one might hope that some similar idea can be used to prove the weak gravity conjecture. And so we are working on this problem. So far, we have found that there are constraints in low energy effective theory of gravitational system that cannot be captured by the standard Wilsonian paradigm. That the absence of global symmetry can be quantified to the distance conjecture. Absence of global symmetry can be quantified and strengthened in the form of weak gravity. And as I showed you that in ADS, we can actually quantify and prove at least part of this conjecture. So this is the first part of this. I only have 10 minutes left. So I will discuss the second exact statement about conformal field theory. So now there is something completely different. Now, if you are over 50, you probably know what this is about. But if you don't know about it, don't worry about it. So I would like to tell you about another line of work that I have been doing, which is to understand the interface in conformal field theory. And somehow this is actually related to my interest in the distance conjecture. Because if you have a conformal manifold, you are interested in understanding conformal field theory at two different points in this conformal manifold. And naturally, you should consider interface. And in fact, there have been an idea by Mike Douglas to use conformal interface to define new notion of distance between conformal fields. So I was interested in that. So because of that, I have been working with these people, Andreas Karch, Yu-Ya Kusuki, and Sungwon Wan, who are Texas in this line of work. So I'd like to tell you a little bit about this. So if you have conformal interface, there are there are many interesting quantities that you can introduce, but the two interesting quantities are effective central charge, which actually measure the amount of entanglement across the conformal interface. And there is another quantity called C left right, which measures the amount of energy transmission across the interface. So what we have done is to propose this inequality between these quantities. That amount of energy transmission is always less than the amount of information transmission. And that is bounded by the central charge of conformal field theory on the two sides of the interface. So let me tell you let me give you a definition of this code. Okay, so first is the C left right. So suppose you have conformal field theory C left and another conformal field theory C right, both are two-dimensional. And there is a conformal interface which preserves half of the conformal symmetry. Namely, that conformal symmetry which preserves this location of this interface. Now, if you consider 2-point function of energy momentum tensor on this side, then the singularity is measured by C left. That is the central charge on the left side. And if you consider 2-point function of energy momentum tensor on this side, you get C right. Now, you can consider 2-point function of energy momentum tensor across this interface. Energy momentum tensor like that. And the normalization of this is given by, defined to be C left right. And it was shown by Maineri, Penedones, and Rosset about 5 years ago that this is actually related to the amount of energy transmission across this interface. And since energy transmission coefficient cannot be greater than 1, so this automatically gives you this inequality. Okay, so C left right, this 2-point function has to be less than either of both central charges on both sides. Okay, so this is this. Now, what we suggested recently that there is actually something in between, and this something in between is effective central charge, and the effective central charge can be defined in the following way. So suppose we consider two-dimensional conformal theory, and this is Cauchy surface of this conformal theory. Let's consider some kind of segment of this Cauchy surface of length L. And then what we do is that take vacuum state of this conformal theory and take density matrix defined by this vacuum, but then take trace over complement of this Cauchy surface. And this defines density matrix. And then you can calculate von Neumann entropy of this density matrix, which is a definition of entanglement entropy of this region. And it's famously this entanglement entropy is given by central charge times log of the distance. So this is a very well-known result. And if there is an interface, this formula can be modified. If the end point of this entangling surface does not touch the interface, then the result is what you expected. But if either one or both ends of this interface entangling surface touch on the interface, then formula is modified. You get some new constant. And this new constant is called C effective. It was not known before that whether this definition of C effective and this definition of C effective are same, but actually we were able to show that these are the same. And now we can actually use idea very similar to the proof of C theorem by Cassini and Welter to actually prove the first part of inequality here. So the idea is the following. So Cassini and Welter in 2006 proved what is called C theorem in conformal field theory. And by using this conformal, the entanglement entropy formula without the interface. And so basically we use the same idea, but with interface with one of this triangle ending on this side. And what you can do is that by using the strong subadditivity property of entanglement entropy, which is I wrote over here, we can combine this inequality with this definition of effective central charge to show this inequality. So therefore, you see that the C effective cannot be greater than C right. And we can do the same for C left. And so from that, we can prove the first part of the inequality. To prove the lower bound of this inequality, well, we have not yet have a proof. We want to prove it. But so far, we have checked it in a variety of conformal field theory. One is a free field theory and their perturbations. And another is a holographic dual construction, where you can actually calculate the entanglement, we can calculate the C effective using this conformal interface, description of conformal interface in the bulk gravitational dual. And from that, you can actually deduce this inequality. So we can, as I showed that this part is already proven. This part, we are still conjecturing it based on example we know of. But I believe this is, it'd be nice to prove it. In particular, this lower bound is very interesting because this means that the amount of energy transmission characterized by C left right is bounded above by the amount of information transmission. So what it means is that if you have a conformal interface, you cannot transmit energy unless you transmit the information. So there must be some information theoretical meaning to this statement. And just like in the previous example, these inequalities are sharp because we can actually come up with an example where these are saturated. Okay, so that's all I wanted to say in this lecture. So I have presented for you two exact results. Exact in the sense that the proposals are exact, and I gave you some physical derivation of these inequalities. And it would be nice to actually make the derivation of this more mathematically precise. And but that's my second lecture. Thank you very much for your attention.
Well, of course, this is a great lecture, and we are very happy to listen to you. So, any questions? Yeah.
Oh, hi. So for the theta gravity or flat space gravity, can we generalize the conclusion here and test the distance?
Sorry, I didn't quite understand the first part. Could you repeat slowly?
Okay. So for the theta quantum gravity and the flat space quantum gravity, do we have some way to generalize the conclusion here and test?
You asked about Dojita holography?
Sorry, the theta.
Dojita holography. Yeah, so I do not know to begin with what Dojita holography is. I do know ADS CFT correspondence, and that's well formulated, and it's an exact statement. There are a variety of proposals for holography in flat space and Dojita space. And I suppose you are referring to proposed holography for Dojita space. Is that what you're referring to?
Just some way to generalize your conclusion to our universe with positive cosmological constant.
Yes. So it's very desirable to generalize this type of exact statement in a situation where cosmological constant vanishes or is positive. This is for cosmological constant negative. And that requires, first of all, understanding what the first principle is for these gravitational theories. So in particular, whether there are holographic description of these space-time. Now, there have been many proposals. For example, Andy Strominger proposed for flat space what's called the celestial holography. And it'd be nice to actually formulate this precisely and understand it. For Dojita space, many people, like for example, people in Stanford had some proposal about how to describe quantum gravity in Dojita space. I understand them less, so I have no comment about this construction. If they can be achieved, then we might consider using that to prove this conjecture. But so far, there is no concrete proposal, so I do not know.
Thank you.
Okay.
So you put up a question mark on the question that's what's the unification for the these weak gravity conjecture and the theta conjecture? And do you have a
so what the Dojita? Sorry, what?
In your lecture you put a question. So you said this generalized
So the question I was proposing is let me see what. Yeah, so the question I was suggesting is this one.
Yeah.
Okay. It's a relation between Dojita, the distance conjecture and weak gravity conjecture.
Yes. So I wonder, do you have any comments or what do you expect? What's the
Yeah. So this is actually what I was doing. So as I mentioned, it seems like there is actually close connection between absence of arbitrary parameters and absence of global symmetry, because you can think of absence of parameter as absence of -1 forms, right? So this is sort of more or less true, and so this leads me to expect that there might be connection between. So now you can see that this is here you have an explicit formula here, but there is an inequality here. There is an equality here, but there is some parameter. So analog of this claim should be the inequality for alpha. So what Ifan and I did was exactly that, because Ifan and I showed that there is an inequality for alpha. So therefore, in some sense, Ifan and I have actually achieved what I wanted to achieve over here. So, right? So, so namely that analog of this, and then if there is actually, well, we have, Ifan and I show that there is an inequality in alpha. It'd be nice to understand the logical connection between this inequality and the inequality of alpha, which is still missing.
Right.
But I think that's what I would like to understand. And I think by understanding the analog of weak gravity, how precisely the weak gravity conjecture can be formulated for -1 form symmetry, probably we can understand. Okay, yeah, thank you.
Other questions? Yeah.
Graphics, or is it?
Sorry?
For the second part of your result, did you restrict yourself to holographic conformal theories, or?
You, so let me make precise statement. So let's go. Let me first. Yeah. So for this, so there are two inequalities here. So this part I have, this inequality applies for any CFT, any unitary CFT, because I proved the only assumption I made in this inequality is a strong subadditivity condition. And this follows from the positivity of the Hilbert space. So therefore, this inequality is true for any unitary conformal fields. This inequality we observed in holographic CFT and free field theory and any conformal field theory that can be obtained by weak perturbation from the free field theory. Okay, so that's the answer to your question. Okay, so I have proven, I have proposed these two inequalities. This is actually, I proved, this apply to any unitary shift. This apply so far only for holographic theories and free field theory and their perturbations.
Yeah.
Thank you. I also have a question about this inequality, about the first inequality.
This part.
Yeah, physically it smells a little bit like some kind of second law.
Yeah, well,
Yeah.
it's some kind of information inequality, right?
Right. So is it possible to like prove this from some like entanglement second law from the field?
Yeah, I think that would be very, very interesting. Yeah, I think that's a very promising idea.
Thank you.
Yeah, it smells very much like the second law of information. Yeah.
Okay. Yeah.
I want to ask a question regarding the proof of the first inequality. Here you mentioned that the CFT will, in the end, in the limit, will become something like Kazhmoudi algebra.
Oh, you're talking about yes. So what I showed is that so I guess you are talking about this part of the.
Yes.
So here what we showed in the second part of the this part of the talk was this part of the talk was that in this limit the CFT contains some subsector on which you can define Kazhmoudi algebra.
You can be derived just purely from CFT.
Yeah. So here is the derivation. So I actually explained the outline of the proof that assuming there is a family of primary field, you can define J, and these J satisfy the Kazhmoudi algebra.
But in the end, they are not actually the Kazhmoudi one because there is no structural constant, right?
Well, it's the abelian Kazhmoudi algebra.
Okay.
Yes. So in general, you can have structure constant, but for those J's associated to operator whose conformal dimension vanishes, the structure constant has to vanish. So it's abelian Kazhmoudi algebra.
Okay, thank you.
Okay.
Yeah, just a precision on when you're in the context of this Cassini-Huerta, now with a regular C theorem. Yeah, now you put the interface at the boundary. I'm just wondering, in the context of this renormalization group laws, was your C effective? Would it obey still all the RG axioms? And
No, well, this inequality itself is an analog of C theorem in this case.
so it would obey the same axiomatics as in Cassini-Huerta, right?
No. Well, it's a different story. So Cassini-Huerta was interested in how C changes. Yeah. So this is this idea of proof applied in different contexts. So we cannot mix them.
Sure. I mean, like axioms should hold for any.
Very much. Yeah, I enjoyed my stay here. Thank you very much for your hospitality. And I really enjoyed this vibrant scientific atmosphere of Tsinghua University. So thank you very much.
So we are expecting you come back again.
Yes, sir. Thank you very much.